Hi guys, this is Mr. Thompson, and today I want to extend on the lesson that we had in class today discussing heat and temperature. Now we're going to go into something called specific heat, and this is where the math really starts to break out in this unit. So I really want you to pay attention, make sure you take good notes on this, and then ask questions in class if you have them tomorrow. So let's get right to it. So we talked earlier today in class about how if I put energy into something, it's going to raise the temperature. But we also kind of explored a little bit about the difference, say, between the energy coming in or going out of a piece of metal versus going in and coming out of a block of wood. And we talked about how the difference between a conductor and an insulator. So now we're going to get a little bit more specific about that. For instance, if I put 1,000 joules of heat into a 100-gram silver fork, then its temperature jumps up about 43 degrees Celsius. And we'll get to how I know that in just a little bit. However, if I put the same amount of heat into 100 grams of water, notice it's the same mass, just a different material, the temperature only jumps up 2.4 degrees Celsius. So, 20 times the difference here. And so, we know that silver is a far better conductor than water. I talked about today how water is a very poor conductor. And what that means, not only does heat transfer in and out of it very easily, but you don't need as much heat to change the temperature of it. And each material can have a different amount of heat it requires, and we're going to give that a special term. We're going to call that the specific heat of a substance. That is the amount of heat required to raise the temperature of a mass of that substance by 1 degree Celsius. Now, I know that definition might be out there a little bit on you, and we're going to explore that just a little bit. But before I jump into that, I want to show you some of the materials that we've been talking about so you can kind of see the difference. These are the specific heats. Remember, specific heat is how easy it is to raise the temperature. So we take something like silver, and you look how small that number is. It doesn't take a lot of energy to raise the temperature of a piece of silver. But if we look up at water, that jumped up there. Again, a little less than 20 times more than silver. So you can see on here some of the materials that we've talked about, how, wood versus concrete. You can see the difference. Wood is about twice as hard to raise the temperature of. The best one by far, gold. Gold conducts heat so very well. Take a look here, animal tissue. That's skin. Our skin is actually not a very good conductor of heat. And so, small amounts of energy aren't going to raise our skin's temperature very much. Continuing on, okay, talking a little bit more about specific heat, it tells us the energy it requires to change the temperature, okay, and that's going to come with a formula. Q, we talked about before, Q is heat, equals mc delta T. M is the mass, C is the specific heat, and we saw a bunch of those on the charts. Don't worry, you're never going to have to memorize one of those. And delta T is the change in temperature. Please pay attention to that. That is the temperature change, not the final temperature, not the start. So there, you've got to find out how much did it change. We're going to take a look at a couple of problems that are going to involve that. This very first one, I'll let you read it. 11,400 joules of heat. We're changing the temperature, okay? And we've got the mass. We want to know what is the specific heat. So we're going to start by writing the formula. In this case, we are solving for specific heat. We are solving for C. So I need to get the other two away. And since they're all being multiplied, that's really simple. All I'm going to do is I'm going to divide both sides by the variables that I don't want, M and delta T. And this causes them to cancel out. So if I rewrite my formula, I've got Q divided by M delta T, which is right where I want. Plug in numbers. Plug it into the calculator. Please make sure that you understand, guys, both of these numbers are on the bottom. So both of them need to be divided. So you're going to take 11,400 divided by 638 divided by 20, and that gives you an answer of 0.893 joules per gram degree Celsius. You don't have to worry too much about the units, but we want to keep correct significant digits, and so all of these had 3, so that's what we want to do. One other thing I want to draw your attention to, I mentioned this earlier, delta T is the change in temperature. Notice that I put 20 here because it went from 10 to 30. So there was a change in temperature of 20 degrees. Let's take a look at one more example. Okay? Again, have the mass. This time I'm given the specific heat. I'm given the initial temperature, and it absorbs 120 joules of energy. What is the final temperature? Okay, so when I look at my formula here, I don't have a final temperature. I have the change in temperature. So I'm going to have to figure out how much the temperature changed and then just add it into this. So let's get started with that. Let's get delta T by itself. I'm going to divide both sides by M and C. Okay, they're going to cancel out. And that's going to leave me with my new formula. I'm going to plug in the numbers from the problem. Again, I've got two things on bottom, so I have to make sure I divide by both of them. Put it in the calculator. 72.3 degrees Celsius. I guarantee you on a quiz or test that will be an answer choice, and it will be wrong because that is the change in temperature. It changed by that much, and so since the original temperature was 13.0 degrees Celsius, the final temperature is going to be this plus this, which gives you 85.3. I hope you wrote everything down. I hope you made some notes, guys, because tomorrow I want to be practicing on this in class, and I want you to be able to complete these problems. They're pretty straightforward, but you've got some information you have to get out of the problem, and they can be a little confusing at first. If you have any questions, feel free to email me or ask me in class tomorrow. You guys have a great evening, and I'll talk to you tomorrow.